choosing the equalizer tabs, let's say. So you are saying it's different for odd and even. So what happens if it's odd? This is the the channel response has odd number of tabs. By 3 you mean something like this? One precursor. So something like this. And what will your equalizer be for this one? And what do you get? If you will get something, so basically these are the two things that you can choose, and you make these to be 0. Okay. Let's say there are 2 post cursor and 1 precursor, and your equalizer will also be similar, is it? So what do you get now? Yeah, you will go from -2 to +3. So these 3 you set to 0, right? I mean, those are the 3 that you can set to 0. I don't think you can make this or this 0 anyhow. Is that okay? Or because you get this plus the absolute values of these also, right? So you get beyond 1 as well. At the sampling point, if it's properly equalized, it should become close to 1. Yeah. That's because the ISI is not completely 0. So when it starts from -2 and goes to +4. So now, so you can't make all 4 0. So I think still you can only make these 3 zeros. Is that no, this is the product of which and which? Equalizer. You can't make this 0. It's only the choice between these 2. So then I would make this one 0 because this would then turn out to be smaller, I think. So see, you can't make the n tab 0. That's with even number of tabs. Yeah, I had not mentioned this in the class. With even number you get, I think actually as you have more, you will have fewer constraints. Right? You have only the number of tabs of the equalizer to choose from, and if you choose the number of tabs of the equalizer exactly equal to number of tabs in the response, then you will have a limited choice. But still, I think the n tabs you cannot make 0 anyhow, and you make the ones closest to the cursor 0. That will leave you with the minimum possible ISI. So far we have looked at linear equalizers, and these can be in the continuous time or the discrete time domain, and also in the receiver or the transmitter side. So far our analysis doesn't make any distinction between any of these cases. And of course the more tabs you have, the better you do in terms of ISI. And we had 2 ways of choosing the tabs. One was to do 0 forcing, and the other one was to minimize the mean square error. And the idea was 0 forcing tries to invert the channel, so it may be bad for noise in some cases, and also for crosstalk and so on. So minimum mean square error does better in presence of noise. That's why we have the 2 techniques. Any questions on any of this? How we came up with the tabs? I mean, you can think of it as part of the equalizer, right? Like if you use an integrator, you add it to the channel and then see what happens. Okay. So the integrating filter is a match filter for rectangular pulses. That's why we use it. So that gives you the optimal signal to noise ratio. Those of you who have done communications know that if you send a pulse for noise, then you have a match filter whose response is the inverted time version of the pulse that you send. In case of a rectangular pulse, that combined response is simply an integrator. Okay, so that will probably be better. Yeah. Also, when you do integration over one time period, like this is for wireless and things like that. So when you integrate over a certain period and then reset the integrator, it has the effect of nulling all the channels whose frequency is inverse of this. Okay. So let's say you have an interference whose one cycle is like this. Then if you integrate it, it goes to 0. So this integrate and dump filter also gives you null set 1 over Ts, 2 over Ts and so on away from the channel. So in case of wireless where you have multiple channels, this is particularly useful because if you have one channel here and another one here, this one not only gives you the best signal to noise ratio for something here, it also kills off all these other channels. Okay. So that's why that is used in wireless communication. So did you guys figure out how the minimum mean square error comes out? I mean, I said you simply minimize this h square with n not being the cursor. So at the end of last class there were some questions about whether this is the right thing or not. Is that okay? Is this correct? Or so when you take the, let's say this is the composite response of the channel, that is H convolved with G. Okay, H is the channel response and this is the equalizer response. Just for illustration, let's say it has 5 taps like this. Then what you get when you send binary data through this channel is, what are the possible values you can get? So each one of these can be weighted with either +1 or -1. So let's say the cursor is weighted with +1. So there are 16 possible combinations for the remaining ones. So each one can be +-1. So you will get some values around 16 different values around f of 0. Okay, you want to take the mean square values of that. And all these will be of the form, so this will be one of the terms, the next one may be, this sign is inverted and so on. Okay, so there are 16 possible things that you get. And you square and add all of these things. And you can always identify pairs of terms where one of the signs is inverted. So you can take this. So this is of the form a minus b square, where a is this part and b is this. Okay, and this is a plus b square, and the sum of these two is 2 of a square plus b square. So you get f of 3 square separately. Similarly, if you go through all of the terms, you simply get the sum of squares of each of those things. Okay. So, I mean, you start off with, you actually have to square the sum of all these terms, but then when you take the sum of all these terms, also go through all the possible combinations, all of these cross terms cancel out and you get only the square terms of each of the impulse response taps. So, you minimize that to minimize the spread around f of 0. Also, each one can be plus or minus 1, so there are 16 possible combinations, and if the bits are random, all of them are equally likely. That is why when we take these, all of these with equal weights, that is the RMS value of the error. Okay. So you have to weight this with the probability of this combination occurring, right? Now we assume that the bits are random, so all combinations are equally likely. So we have to take sum of all of these divided by 16 to get the RMS, to get the mean square value. So the result will be, and you minimize this and you minimize this, the spread of this cluster of points around f of 0, and that's what you want for maximum eye opening. Okay. Okay, now that we have some way of determining the taps of the equalizer, let's see how to implement it. Okay. And we'll again talk about only discrete time equalizers because that's what we have dealt with so far, but we can also make continuous time equalizers similarly. The principle is always similar, meaning you want to get a high pass response. So we have digital data, and then we can have a discrete time equalizer here and send it to the channel. I mean, we have the transmit pulse also, and we have a sampler, and we can also have a discrete time equalizer here. Let's say we want to use one of these two. I'll show it in both places. Let's figure out which one to use. The slicer is not clear. What I drew here was a comparator or a decision slicer. So what are the arguments for using the field equalizer here or here? Let's say I decide to use it in the transmitter. What are the implications? Or I use it in the receiver. What are the implications? Okay, so what is the implication of that? You are saying that the amplitude here will become too large. Okay, so what does it mean? So let's just say that the transmit amplitude can be large for now. Okay, either this or you scale down the whole thing and you have to receive a small signal. Okay, what else is a possible factor that would let you decide between using the equalizer in the transmitter or the receiver? Yeah, but we saw that if you have channels which are identical, then the effect of crosstalk and all those things are the same whether you use the equalizer in the receiver or the transmitter. Okay. So, but actually even there it is about the same. But anyway, let me write that. So, receive equalizer amplifies noise. This is random noise. And let's say this is not a big factor. Yeah, so we will have to operate within the nonlinearities. That is, we have to always reduce the amplitude so that nonlinearities are not exercised. What is, let's say we have an unknown, varying channel. What do we have to do? We have to adapt. We have to adjust the taps of the equalizer. So, does it make any difference if the equalizer in the transmitter or the receiver? See, basically we have to adjust the taps of the equalizer based on what we see at the output of the channel and equalizer. You can put the channel and equalizer in any order, but you have to look at the output of the cascade of the channel and the equalizer and look at the response and somehow adjust it. How we look and how we adjust is different, but that's where we have to look. Okay, we can't see here and then decide whether the channel is bad. We can only look here or here. Let's say you have the equalizer in the transmitter, we have to look at the output of the channel. If we have the equalizer only in the receiver, then we can look at the output of the equalizer. Okay. So if we have the equalizer in the receiver, then we can look at the output of the equalizer and adjust the taps of the equalizer. But if we have it only in the transmitter, then we can only look at the signal on the receiver side and we have to somehow send back information to the transmitter side to adjust its taps. And this transmitter and receiver may not be at the same place. That's the idea, right? That's why you have the transmitter and the receiver. Firstly, okay, there are certain channels in which you use the same pair of wires in both directions. But how do you start off? Okay, there has to be some information that is going the other way, just for adaptation. Okay, that is not for useful data. Basically, you want to see that the samples. We have not said how to do adaptation and so on. But in a perfectly equalized channel, what do you see? If you sample it, you will see either some +1 or -1. That +1 or -1 are logic levels that can correspond to some voltage level. So let's say plus 300 millivolts and minus 300 millivolts. So you look at the samples, if they're all in the same place, they're all the same value, then it's equalized. If not, it's not equalized. So you don't need any other reference. You can do blind equalization. Okay, you just look at the received symbols, the analog values corresponding to the received samples, and if they are not all the same, that's not equalized. That's period, right? So if you have a receive equalizer, adaptation is easier, simply because the signal you want to see and adapt is at the same place as the equalizer. In the transmit case, adaptation is more difficult. You need what is known as a back channel for adaptation. Back channel is simply some channel that will transmit data the other way, that provides information about what you have to do with the transmit equalizer coefficients. This is the data transmitted from the receiver to the transmitter to adjust the equalizer. But eventually, whatever you do, this is the picture you have to see, right? If it is properly equalized, I want to see a single analog value corresponding to any symbol. So every time I sample, I should see the same. Okay, I should see either plus or minus in case of binary data. But I can't, if I have some things like this, I already know that it is not equalized because that has intersymbol interference, isn't it? So if you see a spread, that means there is intersymbol interference. How we actually go and tweak the equalizer taps, well, let's see. But somehow, let's say you can assign all possible values to all equalizer taps. You try everything and then you make this equal this one value. Or at the very least, you have to minimize the spread of values. What else? When is it better to put it in the transmitter? If the noise added, yeah. Then what else? Okay, let's take some basic thing which is very important for implementation. All these things are important that we listed, but there is something even more important. What's the type of signal that the equalizer sees at its input? How would we make an equalizer? So let's say we want to make a 4-tap equalizer. How would we go about making it? I want to realize an impulse response like this. This is perhaps negative, but this has a cursor and 2 taps, not 4 taps. How will I go and make this? What is the block diagram corresponding to this? So this is delayed, right? You need to have the appropriate delays. This is basically Z inverse if you write it in the Z domain. And if this is G0, G1, G2, you multiply it with a factor G0, this is G0, G1, and sum them all up. How will you realize these delays? You can use flip-flop to delay signals. Under what conditions? What kind of input do you have to see? When can you, what kind of data can you delay with a flip-flop? Digital data. So if the data is plus minus 1, you can do it with a flip-flop. If it's not plus minus 1, so okay, can you use that? Is the data plus minus 1? It's not plus minus 1. So can we use flip-flops anywhere here? So if we use it in the transmitter, the input data is plus minus 1. So in here, we can use we can use flip-flops to realize delays. What about here? What are the kinds of values that you see? It can be anything, right? I mean, in case of 10% eye opening, you saw that it was somewhere between 0.1 and 1 or some huge values, 0.1 and 1.9 or so. So you see analog values here at the input, and you see digital values at the input of the transmit equalizer. The receive equalizer sees analog inputs. How would you delay an analog input? Transmission line, yeah, that's one idea. So digital data can be delayed using flip-flops. Analog data can be delayed using transmission lines. Can you use something else also to delay it? What else can you use to delay analog data? Can we use sample and holds to delay the analog data? So we can, right? So if we, especially in this particular case, we are dealing with sample data. So if we have a cascade of sample and holds, if the second one samples when the first one is holding, it samples the previous data. Okay? So the sampling and holding of the consecutive sample and holds should be, this one means a buffer, it's an amplifier of gain 1. So the sampling and holding of successive stages should be alternating. In that case, you can use sample and hold to delay the data. So you will make a sample and hold like this, and the switch is on for part of the cycle and off for the other part. So the input is, let's say, sinusoid. The output will follow the input for some part, will be held for some other part, and so on. So the next one that follows this, we have a buffer, and this should be sampled with a different phase. Okay, then it will track this, isn't it? So if we have alternating ones, then the successive ones will be delayed versions of each other. Okay, ultimately you will get samples which are something like this from the first one, from the second one which samples the last value of this. So you need to have them alternating in order to get this effect. And what else can you use? How will that, all that is similar to a filter. A buffer will delay it because it has some first order type of filter response, and that's where you get the delay from. And you can do the ultimate brute force thing. You use an analog to digital converter and use digital delays. So you don't have binary values, but then whatever resolution, whatever analog data you have, you convert it to digital with some resolution, and then you can delay the digital data, again using flip-flops. Maybe it is not efficient, but that will also work. So from all this, is it easier to put from this particular point of view, from the implementation point of view, is it easier to have the equalizer in the receiver or the transmitter? Transmitter. Because you can use flip-flops to delay the data, and then you can sum them. Okay? Yeah, that's right. As far as adaptation is concerned, that's a different issue. It's harder to adapt an equalizer when it's at the transmitter. But just to implement the equalizer, so let's say now we are talking about a fixed channel, then it's easier to implement it in the transmitter. What to do about adaptation, we can see afterwards. Okay? It's easier to implement the equalizer in the transmitter. How do we do this? So let's say this is the equalizer I want. Okay, there is one precursor tap and two post cursor taps. How many flip-flops do I need? 3 flip-flops. Yeah, the total span is 3. So with 3 flip-flops we should be able to do it. So I am showing single-ended signals, but you can imagine these to be your CML flip-flops that you design. And all of them trigger on the same edge. So the delay between successive values is 1 cycle. Okay. So will this work? So now what do I have? I have the input delayed by 1 cycle, 2 cycles and 3 cycles. Okay. What do we do about it? Where do we take the output? We need to form a weighted summation of these things, right? That's the equalizer. So this is, so far this has just provided delayed versions. And in fact this, the input corresponds to the precursor, and the next one is this, and the next one is this, and the last one is this one. So you form a weighted summation of these to get this. So what do you assume for the input data in this case, if this has to work? If all the signals have to be separated by 1 cycle of the clock? No, the input itself has to come from a rising edge triggered flip-flop, right? That's what I mean. So, for instance, if this changes arbitrarily, if the input changes arbitrarily, these three will still be spaced by one cycle, but the spacing between this and this will not be one cycle of the clock. Okay. So to ensure that it works properly, we don't use 3 flip-flops, but we use 4. Okay. So now the timing on this is not constrained. It can be anything. It can be anything subject to the constraint that the flip-flop itself works properly. Okay. Now we have these 4 signals, which are 1 clock cycle apart. That is 1 TS apart. Okay. We use 4 flip-flops so that the timing is accurate. Okay. Then what do we do with this? I have generated these 4 and I want to get this. What do I do? How do I make the weighted summation? No, I mean the implementation of the weighted summation. I already know the values of these, let's say, and I want to implement the weighted summation. What do I do? You can imagine CML flip-flops in these, for these, in which case each of these lines is differential, the clock, data and Q. Okay. If you want, you can imagine that. So tell me how we will implement the weighted summation. What are all the ways of implementing weighted summations? Let's say I have voltages V1, V2, V3, V4, and I want to get summing digital to analog converter, summing integrator. What is the principle behind the summing integrator? So in general, when you want to add, it's easiest to add currents. Okay. Generally, why is it? Why is it easier to add currents and not voltages? I mean, to add voltages, you need to put things in series, which is more difficult than connecting all of them together, in which case you add currents. For instance, if you implemented this, this will implement a weighted summation of V1, V2, V3, V4. But this may not be how we implement the transmitter, but this is one way to implement it. So the classic weighted summation is implemented using an op-amp and 4 resistors. So let's say this is some conductance alpha 1G, alpha 2G, and the feedback is a conductance G. What is the output? What is the output voltage here? So the minus V out is alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 plus alpha 4 V4. Is this the kind of amplifier we would like to implement in this equalizer? Is this the kind of weighted summation block that we want to use? I mean, that's what you do want. You want this plus this plus this plus this weighted by some weights. Okay, let's take a concrete example. You've all been working with 1 gigabits per second data in your assignments. What kind of an op-amp would you need to do this? What are the figures of merit of an op-amp? Most important one is the unity gain frequency. What should be the unity gain frequency of this op-amp? I mean, just guess like wildly, what would be the unity gain frequency? It's very great, definitely greater than 1 gigahertz. How would you decide exactly how much it is? Okay, let's say this op-amp can be modeled as an ideal integrator whose response is omega v by s. Have you guys done these things? You know what an ideal integrator model of an op-amp is? Okay, you assume infinite DC gain. You assume that it has a certain finite unity gain frequency. So what will be the response of this? If I apply a step at V1, what kind of response do I see? I have just this circuit. This is a single input, single output circuit. And the op-amp can be modeled as omega u by s. I mean, there is nothing mysterious about this. You are familiar with this model, DC gain by 1 plus the pole. And I neglect this 1, assuming that omega d is very small. Then I get A naught omega d by s. So that's what this A naught times omega d is the unity gain frequency. What is the response I get from this? RC. What is the time constant? Omega r. I apply a step, what do I see? Just tell me that. I apply a step that goes from 0 to 1 volts. What do I see at the output? What is the transfer function between the input and the output? 1 by s plus omega u by 2. Omega u on top. Is this correct? What is the DC gain of this? So this is minus, it's really, the DC gain is minus 1 and The pole is at omega u by 2. So what is the response I would see? What's the step response of this? If I plot the response, it will go in the opposite direction because it has a DC gain of -1. That's not a significant factor. And what is the slope? What is the slope? Okay, think about it. Just work out how much time is required. So I want to say, if I see an input, if I drive at the input with a step, I want to see an output step. I know that that's not going to happen. So I'll approximate it. I'll say that if this is my symbol period, it has to settle to 99% in one symbol period. And the input data is at 1 gigabit per second. Find out omega u. And not for this circuit, but for the equalizer. For this circuit, let's say alpha 1 is minus 0.25, alpha 2 is 1, alpha 3 is 0.5, and alpha 4 is 0.25. So for these values, find out what omega u is, and the conditions are: I want to operate at 1 gigabits per second, and I want 99% settling in 1 bit period. Okay. You find out the unity gain frequency of the op amp, which will help me make this equalizer. We'll continue with this tomorrow.